unfreeze this. Okay, so for instance, if you want to know the mass of CaCl2, this is number 2 on page 7. And again, you should already have this done. What we need to do is find the masses of the individual atoms and then multiply if appropriate. So this is 1 calcium and there's 2 chlorines. When it comes to their masses on the periodic table, what I like to do is round them to 2 digits past the decimal. That's just a nice, consistent thing to do, so we're all doing something consistent. So for calcium, it's 40.08. That's calcium's mass. And then for chlorine, I would take 35.45, but I would multiply that times 2 because of these 2 chlorines right here. And I'm going to get 70. And you're going to vary a little bit in these molar masses sometimes, depending on how you round and all that. That's not a huge deal, but hopefully we're somewhere close. And then the unit for molar mass is G/m, grams per mole. So that's CaCl2. And again, I'm just going to do a couple of these because hopefully you've already done some other practice. And plus, we'll be doing some practice. I remember one of the most missed questions the last time we had a final, which was not last year, was a question that simply asked you to find the mass of something like this. What people mess up is kind of understanding the fact that the 2 applies to the aluminum. So, for example, aluminum's mass is 26.98. I would multiply that times 2. And then we got to remember that this 3 is kind of distributed where there's 3 sulfurs and 12 oxygens. So remember, there's like an invisible 1 there. 3 times 1 is 3. 3 times 4 is 12. So I'd add in the mass of 3 sulfurs. So sulfur is 32.07. times 3 plus oxygen's mass. Now, oxygen, you can call it 16 or you could call it 15.99. It's not going to make a huge difference. But like for this one, we should get somewhere in the neighborhood of 342.17. Last thing I want to mention really quickly is 9 and 10. It says nitrogen gas and oxygen gas. The thing we have to remember here, and I believe we've talked about this a little bit, Brinkelhoff, right? Does that look familiar? Kind of? Okay. Well, I think I talked about it before, but I don't know. Brinkelhoff, Mr. Brinkelhoff, that's like a man's name. And it indicates the 7 diatomic elements, BRINCLHOF. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. What I'm telling you is that, like oxygen, for example, the oxygen in this room is not individual oxygen atoms, rather it's O2. Same with the nitrogen. So this, and same with bromine, if there was bromine in this room, or chlorine, or anything like that. And that's a way to remember the 7 diatomic elements. So what I'm saying is, like, when it says nitrogen gas, number 9, the little bit tricky thing about that is we should be thinking of it as N2.
Will it always be like O2 and N2, something like that? Like, will always be 2 after it says?
What I'm saying is, if you're talking about the element nitrogen and someone says the molar mass of nitrogen gas, yeah, they mean for it needs to be doubled like that.
Okay, it would be like number 3 or 4 or something like that.
Not if it's now it could be in a compound. Like you could have oxygen in a compound, for example, and have 3 of them. But I'm talking not when it's the pure element oxygen, it's going to exist as O2. Okay, so all that said, turn to the next page. When we were doing unit conversions earlier, one of the reasons, like remotely, I think when we were doing this, one of the reasons was because we can use dimensional analysis to solve the problems that are on this page. The thing that says grams to moles. This is one of your most like bare bones skills in chemistry, is converting between grams and moles. Because here's the thing, okay? Our next unit is going to be chemical reactions, and then from there we're going to go on to talk about how one could predict the results of chemical reactions chemical reactions deal with atoms and molecules, which of course are very, very small, but we want to know how many of them that there are. The only way to do that is by weighing them, because clearly we can't count them. So we can kind of count them by weighing them. So we can weigh them and we can know how many atoms there are, or vice versa. So being able to convert from grams, which is nice because you can just put something on a scale and weigh it, to moles, it converts to a number of things. It ends up being super useful for like a bunch of different stuff that we're going to do down the road. So, I forgot. I probably should be sitting in front of this. So here's how you do it. Okay, so in the top, notice we mean given a number of grams, we're going to convert it to moles. So this is page 8 from the packet that I gave you. So it says 34 grams of NH3, and the instructions tell us we need to turn this to moles. So the first thing we need to do is we need to figure out what 1 mole would weigh. And to do that, I'm going to look at the periodic table. So I see nitrogen's mass is 14.01. Again, I like to round these to 2 digits past the decimal. Hydrogen's mass, if you look at hydrogen, it's like 1.008, something like that. So 2 past the decimal would be 1.01 for hydrogen's mass, but we're going to multiply that by 3. Now, if you call hydrogen 1 exactly, it's not a huge deal, or it's not a very big deal to call nitrogen 14 exactly either, but sometimes it does make a difference. Anyway, just for consistency's sake, I like to do 2 digits past the decimal always. So, let's think of what we figured out. This is what 1 mole would weigh, 17.04 grams. So I can change this into a conversion factor. This is a true fact. 17.04 grams is the mass of 1 mole of NH3. And so I can use dimensional analysis to solve this problem. There's other ways to do it, but I can do it. So when we do dimensional analysis, start with the thing you're trying to convert. So the thing from the problem that you're trying to convert always goes first. And we're going to do one of these little train track thingies. My little conversion factor, I'm going to follow the what goes up must come down rule. Notice how I'm attaching units to everything. Really critical that you do that. I'm going to follow the what goes up must come down rule. I'm going to put those grams on the bottom and put the moles on top. And I think I get something like 1.995, something like that. Yeah, rounding it to 2, especially for significant figures, is totally appropriate. Now, when we should always see if our answer makes sense. And it should, because we're saying that 1 mole weighs 17 grams. At the very least, we should probably check to see if our answer, we would expect it to be greater or smaller than 1, or at least get some kind of feel for that. And that does make sense, because a mole weighs 17 grams. We've got 34 grams. That's about twice as much. Now, this way of solving this problem, I think I mentioned before, like when I was a kid in high school, like I did not like this dimensional analysis. But on the other hand, it was obvious to me that for this problem, I needed to do 34 divided by 17. That was just completely clear to me. It just made sense. If it doesn't make sense to you, then you need to do this dimensional analysis. But if it makes sense to you that, oh, yeah, I definitely need to divide here and, get it that way, that's fine. I just want you to understand that I'm always going to solve problems with dimensional analysis when we do them. Let's look at another example. So, number 2. It says 51.40 grams Na2O. Okay, so again, the first step that we got to do here is we got to add up the molar mass of this Na2O. So sodium's mass is, if we round it 2 past the decimal, is about 22.99 grams. But there's 2 of those. So I got to multiply that by 2. And then I got to add that to oxygen's mass, which we can call 16. And we're going to get about 61.98, I believe. Now I can change that into a conversion factor because this is a true fact. So it's just like the last one, 51.40 grams. Always start up here with what you're trying to convert. Do the what goes up must come down rule. And it is, okay, before we even go any further. So this problem is saying I have 51.4 grams. A mole weighs 61.98 grams. Do I have more than a mole here or less? Less. We should get an answer less than 1 here. This might stop you from doing some of the most common mistakes, which would be dividing backwards or even multiplying these two numbers when you should be dividing them. But yeah, it should be 54.10 divided by 61.98. We can have 4 sig figs here. It's something like 0.8293. Now again, you know, I did post the key to Schoology. If you're looking later, if your answers are varying from these by a little bit in the last digit, that's going to happen due to rounding. But that's kind of the ballpark that we want to be in. Questions about those two? I'm going to do some from the bottom, but one thing I would say real quick is if you notice the next one, it gives you in a unit of kilograms. It's not really going to work. We're going to have to make some adjustments. You could do a couple different things, but the easiest thing might be to convert this to grams. So King Hector died by, we got to go from kilo down to the base. We're moving it 3 times. So that's going to be similar to the last couple problems, but it's about 4,500 grams for number 3. Let's look at a couple from the bottom, though. So number 8. 17.1 moles of H2O. All right, so again, what this is asking me is what would 17.1 moles of H2O weigh? To do that, I need to know what 1 mole weighs. So the periodic table can tell me hydrogen's mass is 1.01, but I multiply it by 2 because of that 2. And to that, I'm going to add water's mass, which we can call 16. This is one of those molar masses that you might end up memorizing. I certainly have because I've seen it.
You're kind of just working at it a little bit backwards, but not really
It's backwards. It's backwards from the first ones, if that's what you mean, because we're doing the opposite thing.
Yeah. But
Yes,
it's still multiply. It's still finding out the grams of the difference.
exactly. It still has the same first step. So, like I said, you know, in high school, I didn't really like dimensional analysis, but it was also very clear to me that I need to be multiplying here. If 1 mole weighs 18.02 grams, then 17.1 weighs 17.1 times as much. But the beauty of dimensional analysis is that it works out the math for us, because now, if we follow the what goes up must come down rule, now the mole is going to go on the bottom, and the 18.02 is going to go on top, which means, yes, we are multiplying. 17.1 times 18.02. And we should be getting somewhere in the neighborhood of 308 grams. Yeah, sure, go ahead. So I'm gonna do at least one more of these. If you feel good about what's going on, you can jump in and just start cranking away here. But let me show at least one more of this type of conversion. So let me see if there's anything. Okay, so number 9 says 0.50 moles of Cr2O3. Okay, so in all of these, well, these particular type of mole conversion problems where we're going from grams to moles or vice versa, I need to add up the molar mass first. So I find chromium on the periodic table. Chromium is about 51.99, but that needs to get multiplied by 2. And then to that, we're going to add oxygen's mass, which is 16 times 3. And so we add that all up. It's right about, actually, I think, we could even call chromium 52, really. I think the person who, I didn't make this key, I think the person who made this key made it 52 even. Same thing. So for every element or compound, we can make that little conversion factor. And so we always start with what the problem gives us, which is moles, which is, in moles is in this case, but follow what goes up must come down. So for my little conversion factor here, I put moles in the bottom. It's basically 152 times 0.5, which is about 76, about 2 sig figs is good. And so I'm always giving the same number of sig figs as the problem gives me to start. And again, sig figs is not the huge issue really, but we could try to get it right. Questions about that? Let's see. I'm trying to think if I want to. So there's a couple numbers there in scientific notation, which we talked about on Monday. You could convert those out of scientific notation. Someday I may show you how to do that on your calculator, but I don't know if I want to do it right now.